So in this video, I'm going to talk about music and musical instruments. So we have to start by reviewing the idea of resonance. So remember that everything is made up, matter is made up of particles, and they're all vibrating at some natural resonant frequency. And if we force a vibration to come in contact with an object, and it has the same frequency as its natural resonant frequency, then it's going to resonate out, or the amplitude is going to increase and get louder. So this is essentially how a musical instrument works. We apply a wave to an air column or to a string, causing that to resonate out and make a loud noise of a specific note. So we're going to trap a standing wave where we get that interference, that constructive and destructive interference, so that it resonates out and rings out a note. Now, for an air column, we're going to be trapping an air wave, but in a instrument like a string instrument, we're going to be trapping a mechanical wave on a metallic string. But in both instances, it's going to be a standing wave. So in terms of music, if we go back and talk about notes, I mentioned in the last video that sound frequency is what pitch is. Well, frequency and pitch actually determines the note that a musical instrument is generating. So if you have a frequency of 262 hertz, that's the note C. 294 hertz is D, and so on and so forth. I mentioned that A 440, so this is A, is 440 hertz. So the frequency is the pitch or the note. And if someone is said to have like perfect vocal pitch, so perfect pitch, that means that they can hit a note and sing out a note that's exactly the frequency of 440 hertz. Now, an octave is when we double or triple the frequency of the note. So if we start with a C, that's at 262 hertz. If I were to double it to 524 hertz, then that would be the first octave. At 786 hertz, it would be the second octave. So it would be the same note, but it would just be a higher pitch of that note. Same thing with A. If I were to double, it would double the octave, or it would double the frequency. And I also could cut it in half. So if I went to 220 hertz, that would make an A that was one octave lower. Now, so like I said, how an instrument works is by capturing a standing wave. And this is a harmonic, it's called, and it rings out a louder note or resonates out a note. And this is done in two different ways, most commonly with instruments, with air columns and with strings. So we have open columns that are open on both ends, so any sort of like woodwind or brass instrument. But we also have closed columns, those would be closed on one end. And we have string instruments like violins, guitars, and things like that, where we can trap the wave on a string. For an air column, this works by forcing, air through a column, and we can effectively change the length of the column, and that will change the note that we play. So with the trombone, you move the arm in and out, and it changes the length of the note, or of the air column changing the note. For like a clarinet or a flute, you're effectively opening and closing holes, changing the length of the air column there. And then for string instruments, you're pinching on the frets of a guitar, or pinching in different positions on the neck of a violin in order to change the note that rings out when you pluck or bow the string. So it's something about the length that effectively determines what note. So I'm going to go over to the Elmo here so we can see how that actually works. And I'm going to start with the idea of open columns. So when you have an open column, it is open on both ends. So this is an open air column. And here is just a standing wave so you get an idea. So this is a one wavelength of a standing wave, where this is the nodes, remember, and these are the antinodes. Now for an open air column, the pressure here and here, the air pressure is the same. So when you trap a note and it resonates out, the first harmonic, or it's also called the fundamental frequency, so this would be the shortest length where the note rings out, is has trapped 1/2 of the wavelength in there. So because of the pressure, you have a node at each end. So the first harmonic, or the fundamental frequency, has a length that is equal to 1/2 the wavelength, right? Now, if we were going to then go to the second harmonic, and sorry, this isn't drawn to scale, but if I were to trap the second harmonic in there, again, we would still want a node at each end. So in this case, we would have doubled. Let me just draw this quick. So I still have a node and a node, but now you can see the second harmonic has one entire wavelength. So the length of the second harmonic is equal to 1 wavelength, right? Now, if we look at open column, or so this is open columns. And this also is how strings work, because strings are the same at each end. So when we pinch a guitar string, it's fixed at both ends, and so you will end up with a note on each end. But a closed column is a little bit different. So a closed air column, if we start with the first harmonic, it is going to be closed down here. So in this case, what ends up happening is we end up with a node at one end and an antinode at the other. So we have sort of like this part of the wave trapped in the air column. So it'll be like this. Okay, and that is actually, if we look here, 1, 2, 3, 4, that would be 1/4 of the wavelength. So for here, the first fundamental frequency would be 1/4 of the wavelength. Right? Now, if we go to the next case, right, if I were to double this, then what I would have would be 1/2 the wavelength. But this, because you'd have 2 fourths, right? But in the case of a closed column, it always has to have an antinode at the other, at one end, and a node at the other. So let me draw this. I gotta kind of think while I do this one. Okay, so here you can see that in this case, I have 3/4 of a wavelength in there. This is actually the third harmonic. For this instance, we don't have a second harmonic because we can't fit 1/2 of a wavelength in the open column because of the pressure. So here we go from first harmonic to third harmonic, and here you go from first to second. Now, effectively, we can calculate the frequency and the velocity using the wave equation. So remember that velocity equals wavelength times frequency. So if we wanted to know the frequency of the note, or if we had the frequency of the note, we can rearrange this equation in terms of column length, right? So if I wanted to calculate over here, using an open column or a string, I would say the frequency at n, where n is the harmonic number, whether it's first or second harmonic, and remember that fundamental frequency is the first, is equal to n, and so I plug the n in here, and I do v over 2l, or 1/2 the wavelength. Okay, so this would be the equation for solving for frequencies and velocities and sound of an open column musical instrument. If we're going to be dealing with a closed column musical instrument, we're going to say that f sub n is equal to n v over 4l, where this is 1/4 of the wavelength because of the amount that can be trapped. So these two equations are essentially the wave equation, but just changed a little bit so that we can take into consideration the length of the air column. And we will be using these equations in the lab in order to solve for the speed of sound in air using what is a resonance tube or a simple homemade instrument.